So as Abhishek said that, okay, it will be like this first week, there will be elementary lectures. So how many of you have come before, like last year, for example? Okay, so there are quite a lot of you, and I guess you still remember the lecture from the last year. So in case you have forgotten something, I am going to just remind it. So it will be basically 3 lectures I am going to give, and please ask a question if you have any doubt. So can you see it here if I write it? Is it okay? What about here somewhere? So you can see up to here, right? Everybody can see it. Okay, so maybe I'll just put a line on that other side also. Is it okay up to here? Okay. So first lecture I'm going to remind you about the Brownian motion. So next lecture in today afternoon, so I'm going to talk about random walk, which is a discrete time, discrete space random process. And in the third lecture, so I'm going to talk about a process in continuous time but in discrete state space. So I'm going to basically talk about something called master equation. And I think all of these lectures will be useful for you in the next week, in the second week of the school. Okay, so let's start with Brownian motion. Yeah, so we'll just start with this one. So all of you know that if you have a very small particle about micron size and if you put it in water, so this motion is zigzag, right? So how many of you seen this motion? Have you seen? None of you? You have seen, okay. So if you have not seen, you should see it. If you just take a microscope, go to some experimentalist lab, go take a microscope, and you can in fact take a water and put some little bit of milk and just see it under the microscope. Or if the lab is fancy, so they will have this micron size particle, so you can just put it in water and you can actually really see this motion, right? So that's the Brownian motion. So that's a motion of a very small particle if you put it in some liquid. That's because all these water molecules are hitting this particle, right? So this particle is big enough compared to all this water molecule, but it's not big enough so that this average, whatever the hitting by these water molecules, this average, it doesn't cancel out, right? So if you take a big ball and if you put it in water, you don't see any zigzag motion, right? So it's small compared to this big ball, but it's fairly big compared to the water molecule, right? So now, so when particle diffuses, so there is something called diffusion coefficient, right? So what I'm going to talk about, something called Einstein relation. So which connects this diffusion coefficient to the other properties of the liquid. For example, what is the temperature of the liquid or what is the friction coefficient of the liquid, right? So what is the derivation? So in fact, it's so you should all read this paper. So it's available now in the English translation. So it's a original paper by Einstein. And it's a very nice paper to read actually, right? So if you have not read it, actually you should read this paper. Okay. So now imagine that if you have some beaker and it's filled with water, and you have this micron size particle, right? And it's under some field. So it can be either gravitational field or if it is an electric charge, this particle has electric charge, you can put an electric field. So it's in some uniform field. Okay, so let's assume that this is your x-axis, and let's say this is your x equal to 0. Okay. So now these particles, it's in some temperature T, so that's temperature is the temperature of the liquid water. So when they move, okay, so it's like an ideal gas, right? Even this micron size particle. So, and if you know that if you have an ideal gas, it exerts some pressure, right? Because I'll assume that, okay, they are not enough, this density is low, so that they still behave like a non-interacting particle, right? So if it is ideal gas, so what is the pressure? So we will know that pressure at a given space, so that's the density times kBT, right? So that's the pressure. It's like PV equal to NK, right? So that's the pressure. So once you have this pressure, so if you just imagine that there is a small volume here, imaginary volume, right? So now, so it will exert a volume of particle, right? So it will exert a force on these particles. So what will be the force per unit volume? Force per unit volume is just minus del P of x del x, right? So you should just look at the pressure here, P of x, here P of x plus dx, and then look at the net force, and in the, then divided by the total volume. So what will you see? That that's the force per unit volume. Okay. Now suppose there is a force on this particle, and each particle feels a force of F, right? So then what is the amount of force due to the external force? So F is the external force. So what will be the force because of this external force on this volume? Per unit volume. So that's basically force times the number of particles divided by the volume, right? So therefore, this is just force times the density. Right? Number of particles divided by the volume is the density. So now, so that's the force due to pressure, this is the force due to external field. Now if you look at these particles, after some time, you see that these particles, they don't have any drift velocity in one direction, right? So this in some kind of equilibrium, right? So if these particles are in equilibrium, so they move in a zigzag motion, but as a whole, you will not see these particles going in one direction, right? So that's the imaginary volume where you have these particles. Right? So that means what? The net force on that volume of particle must be equal to 0, right? So therefore, this force plus this force, it has to be equal to 0. So this one, if my density is, if my temperature is constant, so this is just kBT del rho x by del x, and this plus this equal to 0, so that gives me a equation. That equation is minus kBT del rho del x plus f times rho of x. This is equal to 0, right? So that's is in some sense called mechanical equilibrium, right? The total force is equal to 0. But the same problem I can also look at in another way. So when you have this, so if you suppose you, so you have a, you remember this, suppose you just put some particle here, right? There's some gas, spray some perfume here. So after some time, the perfume spreads, right? So if I just spray some perfume here, it will take some time. After some time, you will smell the perfume, right? So why does it spread? It spreads because of diffusion, right? So therefore, if I just spray the perfume here and keep some surface here, so I can find out how many perfume molecules are going or particles are going across the surface, right? So that will be the current. So what will be that current? So there will be a diffusion current, right? So what is the diffusion current? So there is a diffusion coefficient D, and then it goes from the high density to low density or low density to high density. The current high to low, so del rho, del x, right? So that's the diffusion current. So basically, if you have somewhere high concentration, you see that basically more particles are going from there, high to low. If you have some low concentration, less particles are coming from this. So that's the diffusion current. But on the other hand, you also have an external force. And if you have a sphere in a water, let's say, and then if you put external force, so what happens to this sphere? It moves, right? So after some time, it reaches a terminal velocity, right? So therefore, there is a current. So what is the terminal velocity? So terminal velocity will be equal to the applied force divided by some friction coefficient, right? So that's the terminal velocity. And if you have a velocity and if you just put against a wall there and those particles are going there, so what will be the current because of this force? So that's the velocity times the number of particle crossing that, so it's basically the number of particle crossing that per unit area. So therefore the current will be, so this will give me a drift current. And drift current will be equal to density of particle times the velocity, right? And velocity is equal to F by gamma, so it's density of particle times F by gamma. So again, in equilibrium, when I just look at this, if I just leave the system after some time and then if I just look at the particles, you will not see again just some particles are drifting in one direction, right? So this is some kind of a steady state. They are still jiggling around, but as a whole, collectively, they are not moving in one direction. So that means the total current again has to be equal to 0, right? So therefore, I have an equation which is the d del rho by del x plus f by gamma rho of x, this is equal to 0. So I have got one equation here, one equation there. So are these two different equations? It's the same object, right, rho. So it describes the same object. So therefore, this equation must be same as this equation. So if that equation is same as this equation, so what you see is that if I just multiply by gamma, so this gamma d must be equal to kBd, right? So it says therefore that 1 and 2 implies that gamma times d is equal to kBd, right? So this d, diffusion coefficient, is something which is related to the fluctuation of the system, right? So diffusion coefficient describes the fluctuation, right? So that's related to something intrinsic about the system, right? So this is this Einstein equation, and which relates basically some fluctuation properties to some dissipative properties of the system, right? So this is something called fluctuation dissipation. You are considering the dilute limit, yes. Yeah. dilute limit for the particles, right? So like for each particle, so that there is no interaction between the particle, right? Medium is dissipative, right? But this dilute limit for the particles, so that this each particle they don't talk to each other, right? So when you consider terminal velocity also work even if you have one particle, right? So even here I am using the somehow dilute limit, because if I have two spheres, they are coming nearby, there will be some lot of interaction between the thing, right? Because one sphere is going, it will probably produce some hydrodynamics, right? So even here it's a dilute limit, right? Medium is water. Medium is a continuum medium, so it has whatever number of water this thing is there, right? So because you don't have any control of the water, you cannot change the density of water, right? Whatever the water you take at a glass of water. If I just take this water at room temperature, that's the water. Huh? It's like a heat bath. It is the heat bath, right? So now we have this diffusion coefficient. So now what we are going to do, so we have this diffusion coefficient in terms of these properties of the medium. So now I am going to relate this diffusion coefficient to some microscopic properties of the system. Okay, so this is 1. Diffusion coefficient microscopic fluxes. Okay. So how do you define a diffusion coefficient? I mean, diffusion coefficient is true for any diffusion system, right? It doesn't have to be this Brownian motion, right? Even if I release some gas here, it diffuses, there is a diffusion coefficient. So what is the definition of a diffusion coefficient? So diffusion coefficient is usually defined by Fick's first law, right? This is essentially this one. It says that there is a diffusive current that's proportional to del rho del x minus del rho del x, and this proportionality constant, if I just want to make it if I want to make it equal, this proportionality constant is just the diffusion coefficient, right? So then there is also a continuity equation, because this particle cannot get destroyed, or it doesn't get created. So there is a continuity equation which is also known as Fick's second law. It says that del rho del t is equal to minus del j diffusion by del x. So I am doing it in one dimension, but you can actually easily generalize to any dimension, right? So this is true for any dimension. So now, if I just combine this equation and this equation, what I get is the diffusion equation. So I'll just substitute this expression for J, and assuming that the D is now space independent, it's a homogeneous system. So then I get the equation del rho del T is equal to D. There is one derivative here, one derivative here. So it gives you del 2 rho del x squared. Right? So that's the diffusion equation. So this is basically, if I have this particle and I just think of it as a collective thing, and I just look at what is the density. If I just release some, if I put all the particles at one point, how does the density relaxes, right? So that's the equation for this density. So now if these particles are independent, right, they don't talk to each other, so these are non-interacting particles. So this density is also equal to probability density, right? So what is the probability density? So instead of saying that, okay, I release all this particle from here at one point, and let's say I'm standing here at some position x, and I look at how many particles are here at time t. So instead of doing that, I can also do another experiment. I just put somebody there, and you said, okay, you just release one particle there, and I'm still standing at x, and find out at time t whether I get a particle here or not, right? Again, I said, okay, release one more particle, and I said, okay, this particle will go somewhere, and I just see, okay, whether I get a particle here or not. So the number of times I do the experiment there, and number of times so let's say n number of times, capital N number of times I do this experiment, and if I take a small region, let's say between x and x plus dx, and count how many particles I receive here, divided by the number of trials, so that will give me probability, right? And divided by the length at which I am looking at this thing, so that will give me a probability density, right? So that one, if they are non-interacting, if I do this, if I put all the particle at once, or if I do this experiment one by one, is the same, right? So therefore, this probability density is related to density. So okay, density usually if we define, okay, rho x dx, if I just integrate, what is the answer? It's just the number of particles, right? So I can also divide a number of particle divided by number of particle. So this equation, if I just divide this equation by 1 over n, is the same equation still, right? So either I can look at the density, or I can also look at the normalized density, right? So this normalized density is in fact same as the probability density, right? So P of xt dx, so what is this object? So this is the probability of finding a particle between x and x plus dx at time t. So this object P of xt and this object is basically same for non-interacting systems, right? So therefore, this P of xt will also satisfy equation. It will satisfy the same equation, right? So it will satisfy the equation which is del P xt del T is equal to d del 2p del x squared. So I can just write down the equation. It says, okay, it will satisfy basically the same equation. But now let's try to derive this equation starting from the microscopy, right? So I know what is the dynamics. These particles are just randomly moving from here to there. So that's the dynamics. So how do I derive this equation? Okay. So let's try to derive this equation. So I want to find out P of x at a time t plus delta t. So it says that at a time t plus delta t, what is the probability density? So this is equal to, see, if I find a particle here at some time, it must be coming from somewhere, it must be somewhere nearby at the previous time step, right? So it must come somewhere from the close by. So it says that, okay, that means that, okay, these particles were, so if I just think of it like a trajectory, so this is my t, this is my x, right? This is how this particle move, and this is at t plus delta t. So it says that, okay, at the previous times, if I suppose I just look at this discrete delta t time steps, right? At this previous time step, it must be somewhere nearby. Let's call it x minus delta x, right? So that's the probability density that it was somewhere nearby. Okay. But then from there to it has to come to that position, right? So there is a probability that in time delta t, it jumps by a amount delta x. And this delta x can be anything, right? So that's the probability density for delta x. So I have to integrate over delta x from minus infinity to plus. Right. So now, okay, I'll not do all the mathematics here. I'll leave lot of steps, and you are supposed to complete those, right? Because I think unless you do the calculations yourself, it's usually things are not very clear, right? So I'll just leave the steps, and so what you do is you expand this in Taylor series, right? So what is the expansion? So this is P of x minus delta x del P del x plus delta x square by 2 del 2P del x square and so on. And compute term by term. So what is the first term? For example, if I take P of x, this is P of x is independent of delta x. And what is this integral then? This is a normalized jump distribution. So phi of delta x d delta x integral from minus infinity to plus infinity, it will give me 1. Just give me 1, right? So therefore this guy is just say that, okay, P of x. This guy will give you what? Font size, okay. So this first one will give you P of x. Okay, T is there, I am not writing, but T is there everywhere. Second one, this guy is independent of delta x. So I have an integral delta x phi times d delta x integral. And if there is no bias, this is an even function, that's an odd function, and if I integrate, that will give me 0, right? So therefore this term will not contribute. The other term will contribute is delta x square average by 2 del 2p del x square plus higher order terms, right? So now I can take this on the other side divided by delta t. So what is the definition of this one? Okay, I'll write down later, okay. So then take delta t going to 0 limit. I take this in on the that side divided by delta t. So what do I get? So I get something like half limit delta x square average by delta t limit delta t going to 0 is 2 del 2p del x square. And higher order terms, right? So now I am saying that this equation is same as that equation. So what is this delta x square definition? Delta x square is equal to minus infinity to plus infinity delta x square phi of delta x d delta x, right? So this is just the variance of this distribution. So now if this equation is same as that equation, so what must happen? So if these are both same, so then D has to be equal to that object, right? So that's equal to limit delta t going to 0, 1 over 2 delta t minus infinity to plus infinity delta x square phi of delta x, right? So this is what we are calling delta x square. So this is a quantity diffusion coefficient. Now you can write down in terms of the microscopic fluctuations. So what is this? So you look at this particle and look at how much it displaces in a small time delta t. You do it many times and you look at the variance, right? You square it. Suppose you look at n times, you look at this square and divide it by n. That's how you will compute, right? So this is something you can actually compute microscopically if you do an experiment, and that will give you the diffusion coefficient. So now if it is the case, if this limit gives you delta t, so you can actually go there and verify that your higher order terms will go to 0 in the limit delta t goes to 0, right? So that you should complete. So in fact that's the exact equation, right? So there are no other terms in the limit delta t, right? Okay. So that's the diffusion coefficient which is given by this. So you have one definition of diffusion coefficient here, another definition of diffusion coefficient there, right? So in fact then if you do measure something, then put it on this side, actually you can get something on the right hand side, right? For example, you can compute Kb, you know that you can write in terms of the gas constant divided by the Avogadro number, right? So therefore by doing an experiment by measuring this diffusion coefficient, you can actually find the Avogadro number, right? And that's the experiment somebody called Zohar did, and he got a Nobel Prize for it, right? Just to measuring that Avogadro number by just doing this experiment, right? Okay, so now, how much time do I have? Still 11, no? Till 11 o'clock, right? Yeah, okay. Okay, so now, so I have this equation. What is that equation? That's the equation. I have this diffusion equation, del P, del T is equal to del square P, del X square. So this is the equation which governs basically how this particle moves, right? Because it just tells you that what is the probability that you find a particle somewhere. But you still have to solve this equation to find, right? So how do you solve this equation? So how many of you know how to solve this equation? All of you know, I guess, right? Okay. Okay, there are many ways you can solve this equation, but I will probably just give you a simple way. Okay. Okay. So there is something called also a characteristic function. Okay. So what is a characteristic function? So given a probability density, you can also write another function. So let's call it P tilde Kt, which is equal to e to the power I kx p of xt dx. So it's essentially the Fourier transform of this one, right? So given this one, so you can always write down p of xt is equal to 1 over 2 pi minus infinity to plus infinity e power minus I kx of kt. Right? So this one is called characteristic function, and this function has as much information as the probability density has. So either you can compute this one or you can compute the other one, and often this is easier to compute, right? So this is what we are going to first find out from here, right? So it's essentially you just take the Fourier transform with respect to x. So if you take a Fourier transform, so you just multiply this equation, let's call this equation, star. So if you just multiply this equation star by e to the power I kx, and integrate over x, what will you get? So left hand side, okay, there is no problem because it's with respect to time and that's k, so it just commute, right. So left hand side what you will get is del p tilde kt by del t, that's equal to the right hand side. So you multiply by e to the power ikx, and whenever you have something e to the power ikx and then some derivative, if you have to compute these integrals, what do? You just integrate it by parts, right. So you keep integrating by parts and use the property that p of x is a function which decays as x goes to infinity. Also its derivative decays when x goes to infinity. So when you integrate by parts, all this first term where this boundary term comes, so those will not contribute. So what you will have is essentially one term will give you one ik, the other one will give you another ik. So this will be just k squared d p tilde of right, that's the equation. So in fact this equation is essentially same as the other equation. So how many of you know how to solve this equation? I guess all of you know, right? This is a first order equation, there is nothing. So what is the answer? So what is the answer? Can somebody tell me the answer? So if you don't know, then just verify it, solve it, okay. So you know this one, so you can just put it there and find out, right. So what is the now, I can also, of course, solve this equation with various initial conditions, but let's solve this equation with a very simple initial condition, which is p of x at time 0 is delta of x, is just starting from x, right? Starting from 0. So wherever you start, you just call that the origin, or you can say x minus x0, right? So then, what is this object? P tilde of k0. I have to compute this one, but this p of x0 is just a delta function, so that will give me just 1, right? So this is just 1. So now what is p of xt? Is 1 over 2 pi minus infinity to plus infinity. So this one is e power minus ikx t, right? Let's say again a Gaussian integral, right? We all know how to do a Gaussian integral, right? So what is a Gaussian integral? E power minus x square by 2 by square root of 2 pi, let's put as sigma square dx, this is equal to 1, right? So that's a normalized Gaussian integral, right? So then you can do this integral, and what is the answer? You will get, check that you should get 4 pi dt e to the power minus x square by 4 check. So this is the answer you should get, okay. please do the integral and then find out basically. Okay. So this is the solution of this equation for a fixed initial condition, in the sense that if I just start from always from the origin, but okay, if I just start from some other initial condition, find the answer for, let's say, 1 p of x0 is delta x minus. So what do you expect? Since you know this answer, I mean, if this is the initial condition, what will be the answer? It's just that because I have just shifted the origin, right? So x, it will be just x minus x naught. But in general, if I have some other initial condition p of x0, let's call it some p0 of x, right? So that's like, even the initial distribution is not localized, but even initially particles are, they are spread and there is a distribution. So you want to find out what is the answer. So you have to go through the same steps, except now this will be different, and just go through it and find the answer, right? So that's a homework. Okay. So now, so this description, whatever I have been saying, so it's in terms of the probabilities now, right? So if I have this particle, what is the probability that I will just find a particle here? If I release a particle from here, what is the probability that I find a particle, right? But you can also describe this particle in terms of their trajectories, right? So this description, whatever this you write in terms of the probabilities, that's called a Fokker-Planck description. But there is another description which is basically described in terms of the dynamics. So that's called the Landsberg description. So let's do that one. Okay. So let's describe it in terms of description, in terms of the actual motion of the particle. So if I want to look at a trajectory, how do I describe this trajectory, right? So if I look at a trajectory, how would it look? So it is t, and suppose that I am just looking at small time step of delta t. This is my x. Suppose wherever I start, I just call that 0. So how will it look? Suppose I am just doing a measurement, right? Every time delta t apart, I am just looking at measurement. So after this delta t, it will be somewhere here, right? I just put a line there. So after some time, again it will move somewhere. So it will be somewhere there. It will go somewhere, maybe it will go somewhere there, maybe it will go somewhere there, somewhere there, right? So this will be like a typical trajectory, right? Imagine that I have this particle, I am looking under the microscope and actually monitoring the trajectory after any small time step delta t. So what I will notice, basically this jumps delta x will be some random variable, right? It will just, so if I just look at this object delta x and divided by delta t, this will be some random number. The slope will be some random slope, right? Because this guy can either go this way, it will be some random slope, right? So now, this, of course, wherever it goes here, so wherever it jumps here doesn't depend on where it was, what was the jump there, right? They are completely independent, right? They don't have any memory, right? So now therefore, to describe this, I have to describe basically what is the properties of this noise. Because left hand side is whatever, delta x by delta t is just slope. To describe this slope, I have to basically describe the properties of this noise, right? So now to describe the properties of this noise, so usually, okay, if I just assume that, okay, this noise is some kind of Gaussian, then describing the first two moments would be enough. So what is the average of this noise, or what is the variance of this noise? Right? So what is the average of this noise? T. So what is this object? This object is delta x by delta t, but this guy is 0, right? Because it's equally probable to go right side, the left side. So therefore, this is equal to 0. So let's look at the variance. So what is the variance? Let's look at the variance here. Delta t at some time t at some time t prime. So this is a noise here, this is a noise there, right? So I look at there. So if t is not equal to t prime, then this is again 0, because that will be related to delta x somewhere here and delta x somewhere there, right? So this is equal to 0 if t is not equal to t prime. On the other hand, if t is equal to t prime, right? If t is equal to t prime, then this is delta t whole square, right? So that if I just use this one, what do I get? 1 by delta t square delta x whole square average, right? I have just substituted this equation. But I know what is delta x square. So what is that one? I have written down somewhere there. What is delta x square? So this is delta t whole square. And what is delta x square? Somewhere there it's gone, I guess, right? That one. No? So this is 2 times delta t. 2 times delta t. So therefore this one, what is this? 2d delta t. So 2d divided by delta t. So the mean is 0. The 2-time correlation, if these 2 times are different, that's 0. But if it is at the same time, it's 2d times delta t. Now I can take delta t going to 0 limit. So what happened? If I take delta t going to 0 limit, what do I get? Average is 0. This is 0, except when t is equal to t prime, that diverges, right? But if I integrate this function over delta t, if I integrate this function over t, so I will be integrating over this thing, right? So when you integrate, what do you get? So if I integrate this object, delta t prime dt prime, so what do I get? This integral is basically a sum, right? Because I have to break this integral into this over these discrete intervals. So for all these guys where this t is different from t prime, it will give me 0, except when it is both are same, it will give me 2d by delta t, but then there is a delta t coming from the integral, delta t, so this gives me 2d, right. So there is a function whose integral is basically 2d times 1, but on the other hand it's 0 everywhere and diverges at one function point, that's a delta function, right, Dirac delta function. So therefore now I can actually take a delta t going to 0 limit to this equation. Where do I write? Let me just write it here. So let's take the limit delta t going to 0. Okay. We will come back to this limit later. So if you take this limit, delta x by delta t becomes dx dt. So this right hand side, I replace it by some other noise. And what is the properties of this noise? What are the properties? It says that is equal to 0 and is equal to 2d delta t minus t. So you should always remember this limit, because suppose you have to, so this is the equation you write down. Now why is this equation useful, apart from you can derive something, but this also equation is useful because if you want to do something in the computer, this is the equation you are going to use. But in a computer you cannot use a continuous time in the sense, right, because you have to discretize time. So when you discretize time, so you basically have to write down that equation. So what is the discretized time equation? So this will be delta x by delta t is equal to, this is your noise with the property that delta tt is equal to 0, delta t at t prime, this is equal to 2d by delta t, right. So if you take the delta t going to limit, 0 limit, you basically come to this equation. Okay. So this equation is called overdamped Lange equation. So what is overdamped? Right? Is there any question? So I say it's an overdamped equation, but okay, let's see what is overdamped. So this particle, these are just classical particles, right? Classical non-relativistic particle, right? And we know that there is only one equation which describes any classical non-relativistic system. So what is that equation? Just Newton's law. So these particles must obey Newton's law, right? So what is the Newton's law? Just says m dv dt is equal to the force. So what are the force? It's in water, so there is a viscous force, so which is minus gamma v, right? And then there is a external, okay, there is a external force. If you put an external force, suppose for the time being assume that there is no external force, right, because even here I didn't put an external force, right, and then there is noise because of this bath, right, so there is a noise. So let me just put a coefficient here to gamma T times some noise. Okay. So this particular way I have put it such that basically it's okay. I'll come back to it later. Okay. So this is the equation I know that it must follow. Right. So now if I take this equation and this equation we can solve, right? Okay, let me just write down this equation in a different way, divided by gamma. So then I have an equation m by gamma dv dt is equal to minus v plus 2 gamma kbt divided by gamma. So it's gamma. Right? So this is essentially, so if I define a time scale which is called m by gamma, so what is the unit of m by gamma? That's the unit of time, right? Because if I divide m by gamma here, this is v by time, so therefore if I divide m by gamma, so m by gamma must be unit of time, right? So this is time scale. dv dt is equal to minus v plus, this one we know, that's 2d times theta. So I know this, okay, you know how to solve this equation, right? It's again a first order equation with a time dependent part on this side. But suppose this side is not there, so what is the solution? Suppose this left hand side, this term was not there. So what is the solution of only this part? V at t is equal to v of 0 e to the power minus t by tau, right? So what is tau then? Tau is a time scale at which whatever initial velocity you took, see after, when t is much larger than tau, this will go to 0 basically, right? So this is basically a viscous time scale. So if you take a particle in a fluid and just give an initial velocity, after some time it gets damped, right? So that's this damping time scale, right? So this is the time scale basically beyond which, if you're looking at your motion beyond this time scale, so you can ignore this term from your equation. So you should find out actually what is this time scale for a particle. So maybe that's a calculation. Find tau for a typical Brownian particle. So what is a typical Brownian particle? Size will be 1 micron. What will be the density? The density will be like similar to the density of water because it just immerses in water. It doesn't float or it doesn't sink, right? So it just stays there. So density is basically roughly equal to the density of water, right? So then just compute what is this time scale. So then you will get a feel basically what is this, how long it takes to actually forget its initial velocity. Right? So you should, given this, now you take this whole equation and you can integrate this equation, right? Because this is a first order equation, no? This is tau dv dt plus v is equal to 2d times theta of t. So you can find out what is v of t, right? Try it. Then you should find out what is v of t average with respect to these properties, and also find out what is V square T average, and then find out the answer when T goes to infinity. Right? So what is the answer? Can you guess the answer? Huh? KBT by M, right? It should equilibrium, right? Okay. So find that answer. Also, this is the equation for velocity. So if you know the velocity, how do you find out the position? X of t minus x of 0, which you can just call it 0, is equal to pt prime dt prime 0 to t by definition, right? Now, you know how to write down this v of t, write down the answer, substitute it here, so then you have x. So given this, find out x of t, find out x square t. Right? So now, see what x squared t gives. So it should have two behaviors. You will see that because your time scale is tau, so there should be one behavior where t is much less than tau, and there is one behavior where t is much greater than tau, right? So what is the, what should you expect? So if it is very small, right, if it is smaller to this time scale, so what is happening? This particle is essentially you give an initial velocity and just it moves. Just x equal to like vt, right? So x square is equal to v0 square average time t. Right? This is how it should behave. And v0 square, what is v0 square? So that you have found out because, okay, this was taking from some initial velocities, but now even initial velocities will be distributed along according to the same law, because this water has been there for, I don't know when they put this water, this experiment, maybe for example here, it has been there for at least 2 hours or 1 hour. So these velocities have already equilibrated, right? So if I just put up, suppose imagine that if I had some particles there, right? This Brownian particle, they had already equilibrated, right? So the velocity there, if I look at the initial velocity, their variance will be this one. So this one, but if it is at a longer time, t square, sorry. So you're saying, say, x equal to v0 t. So that's a ballistic motion. But now if you look at a very long time, so again, whatever exact equation you have, exact expression you have, you should verify that it should give you the answer 2d times t. So it basically have this diffusivity. So this is this overdamped limit, right? This tau, when your time scale is greater than this tau. So this equation, whatever equation we wrote down, this delta t going to 0 limit. So this 0 is essentially like some quantity which is much bigger than tau, right? But much smaller than your observation time. Right? When you say in physics, when you take a limit, 0 is not always 0, right? It just depends on sometimes for some 10 to the power minus 2 might be 0, or for some cases 10 to the power minus 5 might be 0, because it depends on what quantity you are comparing with, right. So 0 means essentially a small number. So if you are looking at the observation time scale, right, which is bigger than this tau, so then this equation is valid. So this is the overdamp limit of the overdamp description of the system. But if you look at the time scale, even smaller than this one, so this equation is not enough. So in fact, you have to take the full equation, right? Okay. Okay. So now another one, maybe exercise again. So you should find out, okay, given this typical particle, I have said that, okay, you are going to compute this time scale for the same particle. So find out how much it will move, let's say in 1 second, right. So what will that be? I said that, okay, delta x square is 2 dt. So typical displacement will go like 2d delta t, 2d delta t, and if delta t is of the order of 1 second, you should find out how much this particle will move. Right? So that will give you a feel basically, okay, what is the motion we are talking about. Okay. So now the last thing, okay. We want to do, so we have written down one Fokker-Planck equation, which is basically the diffusion equation, which is in a free space. But how do you generally write down a diffusion equation? Sorry, Fokker-Planck equation, right? So in general, how do you describe a Fokker-Planck equation? So Fokker-Planck equation is, you can only write down for something called a Markov process. So Markov process is a process basically, if you want to write down the probability distribution at the given instant, it only depends on the whatever the probability distribution at the previous instant. It doesn't depend on the whole history, right? So those are called Markov processes. So in terms of the Lange equation, basically what it means is that your Lange equation is first order equation. It will not have second order time derivative, right? Like for example, this equation I have write down dx dt equal to something. So that's a first order equation, right? So now this one, if I want to write down in x, this will be d2x dt2 dx dt or something, right? So this is a second order in t. So given this equation, I cannot write down a Fokker-Planck equation directly in x variable, because it will be not a Markov process in x variable. But on the other hand, if I just write down the same equation in two variable, one is x and one is v, so then I have an equation which is called, which will be dx dt equal to v, and v satisfies this equation. But both are now first order equation, right, in time. So given xv at one point, immediately I can find out what is the x and v at the next point, right. So I need both x and v. So therefore, to write down a Fokker-Planck equation for this one, I have to consider both x and v at the same time. Right? So now let's consider some set of variable. Let's call it y1, y2, I don't know, yn. In this case, one can be x and other can be v, right? So this is a Markov process, and I want to derive a Fokker-Planck equation for this variable y. So given this, how does this y? So I'll go again do the same trick. So what was that? T plus delta t. this, since it's a Markov process, it just depends on what is this guy at time t. So that's p y minus delta y at time t. Then my this jump distribution of making a jump of delta y, but in that case I didn't specify, I just said okay, it just makes a jump of delta y. I didn't say from where it makes the jump, right? But in general, if you have some potential or something, it also depends from where it makes the jump. So in general, it also depends on the initial position. So it will be function y minus delta y. So given y minus delta y, it just makes a jump of delta y. Huh? Some variable, let's say in this case, these are some random variables. So when you take them as a complete this and together, then you have a column vector y, and that is a Markov process. For example, here in this case, there are two variables n equal to 2, one is x and other is v. This is for general Markov process. So if I have to go from here to here, I have to just choose n equal to 2 and just put 1 equal to x and 2 equal to v, right? And then I have to take a integral of delta y. This is an n-dimensional integral of delta y. These are all d of delta y, and that's all, right? Now I'll do the same trick. What did I do there? I expanded in Taylor series, right? But now here when I expand in Taylor series, okay, this is also a function of y minus delta y, this is also a function of y minus delta y. So I have to expand both. So the convenient way to, you can of course expand this and try to combine all these things, it will give you the same answer. But a convenient way to expand both will be, I just call something at another function y minus delta y, which is just the product of this, and this function I can just expand in Taylor series, right? So again expand this in Taylor series, g of y plus a minus sign, so minus I equal to 1 to n delta y I del g del y I plus half I equal to 1 to n j equal to 1 to n delta y I delta y j del to g delta y I, sorry, delta y I, y j, and so on, right? It's a similar expansion what I did before, right? So now put this thing here term by term. What is g of y? G of y is just p of y times phi of this thing at y. So p of y doesn't depend on delta y. Again, I can just do this integral, right? Please complete all the steps, right? I'm not going to finish all the steps here. So the first guy will simply give you p of y at t, right? Because this guy is just p times phi, and p I can take it out and just the integral over phi, that was 1. So it is same as what we did before, right? Second one, what does it give? Second one See, what is Z? Z is this time this one, right? So Z has a phi which is a function of delta y. There is a delta y here, and the integral is over delta y and the derivative is over y. So these are different variables, right? This delta y over which your integration is, and this yi, these are independent variables, right? So therefore I can take this variable, this integral outside. So when I do this integral over delta y, so I will have this integral. What is this integral? Let's write down one of this integral. So I have, let's say, d delta y I. There are n integrals, or others one I am just keeping it outside, times delta y I del y I of z, which is p of yt times phi of delta y, right? So now I have this integral over delta y. This phi, I cannot take it out of this differential because it also depends on y, right? So I cannot simply take out phi outside. On the other hand, this one I can take it outside. So this is equal to del yi. Then I have this integral d delta yi phi of delta y, and this p, it doesn't depend on delta y. I can take it on the other side. I cannot take out from this derivative, right? So this is p of yt. So what is this object? It's just the average over delta y, right? So this guy just gives me the average over delta y. Similarly, when I go to these variables, I can take these derivatives outside. P always I have to keep it on the right side, right? And do this, so it will be basically give me something like this one inside the derivative, right? So that's very important to keep. Okay, so finally check. So you should work it out, and if there is some problem, you can just tell me during the tutorial. So what you find that del p yt del t, this is equal to minus I equal to 1 to n. So this is essentially coming from this guy after those integrals. Del yi del yi average divided by delta t, because I have to take and divide it by delta t, right, to get this one, times p of yt, right, this is what I have. And then I have this other term, I equal to 1 to n, j equal to 1 to n, del 2 del yi del yj del yi del yj divided by delta t times p of yt, and then this guys, when I divide this delta t, so what you have to keep the limit, mind that you have to take the limit delta t going to 0, right. So this is defined with the limit delta t going to 0. And you should again verify that basically all these higher order terms will be basically 0. Right? So that's the general Fokker-Planck equation you have. Okay. So now, so that's the general Fokker-Planck equation. Now let's take a particular case, and let's take the case which was overdamped equation. So what was the overdamped equation? So what was the overdamped equation? So gamma dx dt is equal to, okay, let's take this gamma on the other side. So if you have some external force, so divided by gamma plus your noise. So earlier I had written down this equation without this term, now this is the term, right? So you discretize this equation because I have to compute those quantities, right? Now my n is equal to just 1, right, because n equal to 1, so it basically just y1 equal to my x. So what is the equation? Del p xt del t, that's equal to minus del x, so this is limit delta t going to 0 by delta t times e of xt plus half x square limit delta t going to 0 delta x square average by delta t e of, right, so this is the equation. Right, I have just kept only one variable there. So this is the equation. And I have to find out this object and this object. And this is where I need the Fokker-Planck equation, right? So now I told you how to discretize this equation. So if you want to discretize this equation, how do you discretize? Delta x by delta t is equal to fx by gamma plus some discrete noise, right? I mean noise over this discrete interval delta t. So what was that delta t? It was 0. Delta t square is equal to 2d by delta t. So what is the order of this guy? So therefore delta x is equal to delta t fx by gamma plus delta t times delta t. So what is the average? So average of the noise is 0, right, because that's the property I have. So what is average delta x? That's equal to delta t times fx by gamma. So I have this quantity here, right? So this quantity is essentially this guy is f of x by gamma. So I have computed this one. So I have to compute this one. So what do I have to do? I have to square it and take average. So delta x, I have to square it and take average. So now there will be a term coming from here, this square, but what will be the order of delta t? Delta t square. So that term will be of order delta t square. There will be a term coming from the cross term, but then also when I take the average of the noise is 0, that will be 0. But again on the other, but even otherwise, what is the order of this term? This noise square goes like 1 over delta t. So the noise goes like 1 over square root of delta t, right? So the order of this term is basically delta t to the power 3 by 2, right? So what is the, how does this strength of the noise, how does it depend on delta t? So it says that goes like 1 over square root of delta t, right? On the average it is 0, but if you look at the fluctuation, on the average it will be of order 1 by square root of delta t, right? But anyway, this when you take the cross term and take the average, anyway the average of the noise is 0, so you don't have to worry. Then this is the square of this term. So what is the square of this term? So the square of this term is delta t square times this one, and this guy is, so therefore this is delta t square times 2d by delta t plus order of delta t square. So this guy gives me 2d delta t, right? So delta x square average is 2d delta t. So when I divide by delta t, so this guy will give me so therefore for this particle in a force, I have an equation which is del p xt del t, that's equal to minus del x by gamma p xt plus this t, I can take it outside, is independent of this. So 2d, 2 cancels, plus d del to p del x square. So that's the Fokker-Planck equation for a single Brownian particle in some force field, right? Okay, so it's already up, I guess. So maybe, okay, I'll just 1 minute, I'll just say, okay, suppose you're, okay, this force, imagine that you have some potential and you can write down this force as a derivative of that potential, right? And imagine that your potential is something so that your u of x goes to infinity as x goes to plus or minus infinity, right? So if that is the case, so what you expect is that, okay, your p of x should vanish as x goes to plus or minus infinity, because you have some potential and it becomes more and more difficult for the particle to go. Also the derivative should vanish, should go to 0 as x goes to plus or minus infinity. So given this, after a long time when if this potential, this particle, after some time this distribution will be time independent, right? Initially you believe this particle that they will evolve, since it's in some potential, so it will be, which is bounded, it will be time independent. So you can look at the steady state solution, which is P of steady state by del T, which is equal to 0. So that's the solution you should look at. So that's the equation which says that the right hand side is equal to 0 at the steady state. And verify that that steady state is equal to or proportional to e to the power minus beta times u of x, which is basically the equilibrium canonical distribution, right? So that's what you should get. So if you have this particle and you are in some stable potential, this particle should equilibrium, right? So you should verify that it goes to this Boltzmann distribution, canonical. Okay? Just take this is equal to 0. So then this guy is, you take the first derivative and use the fact that your current is also 0 at the boundary, right? Actually, yeah, total current should be 0. Your total current is 0 at the boundary, so that current is basically that if you just write down del x, so this is minus fx by gamma Ex plus d del p del x. That's the total current. So this total current should be 0. So therefore what you have is that this is equal to 0. And your f is given by this one. So you can easily verify that this p is basically given by this. Okay, I'll stop here.